Thank you. The Elm homepage describes it as a delightful language. And I really like that description because it focuses on the experience of using it, not just the end result or the technical aspects. But it also describes it as a language for web apps, which is practically just begging the question, can you do other things with it too? So my name's Anthony. I like working with robots. These are my credentials. I went to school and stuff too, but this is when I was learning by doing. At the time, long ago for my birthday, I got a Lego robotics kit, and that was probably one of the most influential things on my career. These days, it's basically a full-blown computer inside a similar form factor. So this is the Lego Mindstorms EV3, and it's a small computer. You have motors, you have sensors. They're all kind of wrapped up inside Lego bricks, and you can program them with this visual flowcharting language where you drag and drop blocks to create this sort of sequence of steps. And then when you click play, it uploads the program to the robot, and the robot starts to move. And that's really, really compelling to kids of all ages because you get this really quick and really physical feedback. And it's really, really satisfying. But maybe the most exciting thing for me is that there's this project called EV3 Dev, which is a Debian distribution that runs on the Lego Mindstorms robots. And so it gives low-level access to all the motors and sensors and devices, and then API bindings, and C and C++, of course, Python, Go, and JavaScript. So if you can run JavaScript on the robot, then you can run any language that compiles to JavaScript. So let's put Elm on a robot. All right, so I have a few questions I want to answer. One of them is, can we use Elm to program a robot? The answer is going to be yes. But is it an effective language? Is it going to work well, or are we going to be kind of swimming against the current? So we'll see about that. And then beyond that, is it a delightful language? It might work well, but are we going to have fun doing that? So here we go. So when I think about robotics, I think about it as these three areas. You have perception, behavior, and control. Perception is all about observing the world, taking all that raw incoming data, and then turning it into a representation that you can reason about. Behavior is where you say, well, now that I understand the world around me, what should I do, and how do I do it? And then control is where you say, well, now that I've decided what I want to do, how do I make motors move and things like that to actually take action? And if we look at the Elm architecture, we can see these concepts right there embedded in the root of your application. Your perception is kind of captured by your message. You're getting incoming data from the outside world. Behavior is kind of the interaction between your model and your update function. The model represents the things that you could understand about the world, and then the update function represents, well, whenever we learn something new through an incoming message, what should we do next? And then view and control are similar because they are, in both cases, that's the main side effect of your application. That's how you actually have an effect on the outside world. If you're a web app, the world you live in is a browser, and you affect it by rendering a page. If you're a robot, the world you live in is a physical world, and you affect it by rendering the desired speeds of motors and things like that. So we can basically just kind of copy that pattern and say, well, what would it look like to apply that architecture to a robot? And the main difference is that instead of having a message type, we have a concrete record for input, because it's not defined by you as the programmer, it's defined by the hardware and the things that you have plugged into the robot. So what's the current value of the light sensor, for instance? And then instead of rendering HTML, we render this output record, which says the speed of the left motor should be this, the speed of the right motor should be that. So we're going to have a simple robot. Before we dig into how this is implemented, we'll see, well, how does it feel to use it? So what I want to do is have this robot just follow a line. And so the line following algorithm is pretty simple. Basically, if the light sensor on the bottom of the robot reads a a bright surface, it'll kind of move in one direction. If it reads a dark surface, it'll move in the other direction. And in that way, it'll sort of zigzag along the way and progress forward. So we'll give this a moment to start up. Are we able to switch the video feed to the projector, or should I use my webcam? We'll let that start. I'm going to switch over to my webcam. And we will. There we go. It's going already. All right. So we're gonna get cozy here. We'll pull this over there, and so there we go. Oh, this is real fun, isn't it? That resolution is not what I had hoped for, but all right. So I'm just going to let that go for a bit and switch back to the slides. So let's look at how that's implemented. So this is the code for that. It really is just simple. Whenever we get new inputs, we say, OK, let's remember the value of that sensor. And then whenever we need to give an output, we just say, well, let's set the motor speeds to values that are proportional to what the sensor is reading. So if the sensor reads a dark surface, then the left motor is going to stop, and the right motor is going to go fast, and vice versa. So does it work? Yes. But how does this work? How is this implemented under the hood? And the answer is ports. So there's no native code or anything, anything hacky like that. It's just we need to bridge between the JavaScript API and the Elm program. So we have a port for inputs, and we have a port for outputs. And then the entry point of the application becomes this platform.worker, which, if you haven't come across it, it's in the Elm core libraries, and it's basically an Elm program, but without a view function. So you get your model and your update and subscriptions, but just no view. And so just to mirror the API of an Elm app, I pass in, here's my init, update, and output functions. And then just let this module handle the ports and subscriptions, subscribe to new inputs. When we get new inputs, we say, OK, let's call the update function that you provided, then call the output function that you provided, and then save the new state of your model, send the outputs through ports. And on the JavaScript side, we set a timer. Every time the timer goes off, in this case, 25 milliseconds, we use the JavaScript APIs to read sensors, bundle up the values, send them through a port. Elm app is going to do its thing, send outputs back. So we subscribe to the outputs port. When we get values, we use the JavaScript APIs to set the speeds of motors. And it's really just that simple. There's just a few more things for debug stuff that I didn't show, but that's about it. So let's do something more with this. Let's push it a little bit further and see how does it feel to use Elm for something that's not totally trivial. So we're going to set a challenge for ourselves. What we want the robot to do is to follow a line around the track. OK, we're doing that OK. And then grab something when it bumps into it. And then when it finds an object and we grab it, we want the robot to take that object and then move it to the outside of the track. Always to the outside, not the inside. So that makes it more interesting because it means the robot needs to know which way it's going. And this is actually a pretty good start for the sort of challenge that we did when I was young doing Lego robotics competitions. The ones we did there were usually a bit more complicated, but we also had about 4 months to prepare. The main difference, though, is that when I did those competitions, there was always a fun story surrounding the scenario. So come with me on this journey. Imagine this oval track is an island, and it's surrounded by shark-infested waters, and the robot needs to go around the coast and then pick up people and feed them to the sharks. Okay. So this is important because it gives the robot a sense of purpose. All right. There we go. So now that we have our motivation, we can go back to these three areas of robotics, perception, behavior, and control. And for each of these aspects, there's going to be some state that we need to maintain. And so that's going to be reflected in our model. Our root model is going to have a perception module, a behavior module, and a control module. And they'll each kind of have their own local state and their own update logic. And this is nice because then when you're wondering, why isn't the robot doing what I think it should be doing, you generally have a good idea of where to start. So the root update function is going to look like this. Every time we get new inputs, and the update function gets called, we update the state of perception, and then we take that updated state, we update our current control logic, and then once we've done that, we pass the current state of perception and control to the behavior module, which says, well, like, what's the kind of larger goal? Like, what am I trying to achieve right now? And that's going to, much like the update function of a typical LMAP, it's going to return both a new behavior, and then maybe it'll return a new control state. So the robot might have been following the line, and then the behavior says, OK, now we're going to stop. So we basically then say, OK, we updated perception, we updated behavior, save those. We updated control, but then we give the behavior module a chance to say, wait, do that instead. So we'll take these one at a time. So perception is all about turning raw data into meaningful information. Your sensors basically give you numbers, numeric data, and we want to turn that into something that is kind of more tangible and meaningful. So there's two things that we need to detect in this. That's doing OK. There's two things that it's going to need to detect. One is, have we encountered an obstacle? And the other one is, what direction are we going around the track? So there's lots of things to measure. The perception module has this record of all the things that the robot is keeping track of, and I'm going to go through a couple of them. Detecting obstacles is pretty easy. There's this, at the front of the robot, there's this bumper with a touch sensor, and that just gives us a true or false. Is the button pressed or not? And this is basically just a Boolean, but we're going to just map it to a different name so that later on in our code, we can say things like, is the bumper pressed? Instead of saying, is bumper true? Because is bumper true isn't really something that you would say to a person when you're describing how this works. So that's simple. Measuring curvature is more complicated because we don't have a sensor that measures the curve of the line. So we need to infer it. So if we think about this, what we can do is, if the motors are going at the same speed, then that means the robot's going straight. If one's going faster, then that means that it's turning. So if we remember, what position were the motors at last update, then this update we can say, OK, how much did the left motor move? How much did the right motor move? What's the difference between those? And then if it's close to 0, then that means we're going straight. If it's positive or negative, that means we're going to the right or the left. And so if we take that value and we look at it over time, what we get is basically this big old mess at the top here. The robot's zigzagging along the line, and so sometimes the delta between the motors is just 0, sometimes it's positive. It's all over the place, and it just looks like noise. But if we take these raw values and then average them over time, we can start to see this pattern where whenever the robot is in the straight area, it's closer to 0, and whenever it's making a left turn, it's oh, there we go. The robot's going off because the lights are down. But whenever we make a right turn, now you can see that the data's all over the place. Actually, could we get the lights up again? Otherwise, this will probably get a little wonky. So once we have this kind of smoothed numeric value of what does the curve look like, we can start to categorize it into qualitative things. So the robot can be going left, right, or straight, or it's possible that we just don't know. And that's a little state machine, and state machines are really, really easy to express with pattern matching. If we're currently going straight and we've passed the lower threshold, then now we're left. If we're going straight and we've passed the upper threshold, then now we're going right. Otherwise, it's in the same state. And then if the robot gets lost, then, well, if it gets lost like it sort of did before, and it's just kind of going in a circle, then we can say, well, we kind of lost the curve, and so we should just go back to the unknown state. So we can kind of add that add that function to our processing pipeline. Let's see, if I go back here and there we go. This white block here, when the robot went off the track, that's where it said, "Oh, I'm making a really hard turn. I think I'm lost. Let's now it's unknown." And you can see before it went between blue is straight, red is right. Sorry, red is left. And then when it went off, I turned the robot around, and now it knows that it's going between straight and right. Okay. So that gives us a measure of the instantaneous curvature of the track, and so now we can use that to categorize, well, what direction are we going overall, clockwise or counterclockwise? And it's possible that we just don't know, so we represent that in our perception record as a maybe travel direction. It would be kind of equivalent to say, well, instead of maybe travel direction, let's just make that type have a third variant of unknown direction. And that would be basically equivalent. And I basically just pick whichever one makes it more convenient to do pattern matching on later when I want to make decisions based on that value. So when we put it all together, if the robot's going left, then that means we're going counterclockwise. Right means we're going clockwise. If we're going straight, then we just say, well, we're going straight, but a moment ago, what were we doing then? Just keep that value. So that kind of lets us build up from, first of all, something that we can't even directly observe, to numeric values that are noisy, and then to symbolic values, to this kind of higher level symbolic value, and all of a sudden we're getting this like larger meaningful bit of information from just raw data. So perception it's often very functional. We're just kind of applying mapping and filtering numbers, but there's also often small state machines, right? We have these thresholds between states, and so there's some information being kept. We need to remember the where were the motors in the last update, and so having a language like Elm makes it very clear exactly what information are you depending on. Perception can also sometimes be really computationally heavy. If you're doing things like computer vision and stuff, that's not really the case here. But it might not be something that you would want to do in JavaScript and by extension Elm. But WebAssembly, you say, and I'm actually really excited to see where that goes. So that brings us to control. So control is all about making things move. And it's like a view function, but it'll be like a slightly stateful view function. So essentially every update cycle, we want to output a new record of what should the motors be doing. So control, it constrains the things that the robot can move. It constrains the things that the robot can do. That representation of what should the speed of each motor be is a little bit lower level than we want to deal with, because they're not, there's these three different values, but they're not totally independent. If you're doing something with the left wheel, then you probably care about what the right wheel is doing as well. So we can represent the control state of the robot with just this custom type and say, well, the robot could be idle. It could be grabbing or releasing an object. It could be following the line. And in some cases, there's a little bit of state associated with those as well. Sometimes it's really trivial. If we're in the idle state, the update logic just says, well, it's basically a no-op. And the output, if we're in the idle state, is just set all the speeds of the motors to 0. So that's trivial. Sometimes it's a little bit more, but basically stateless. If we're in the follow line control state, then we don't need to remember any information, but we do just need to know what's the current value of perception. So there's no, again, the update is a no-up, but the output is just this pure function from input to output. Sometimes there's a little bit of state, like if we're grabbing an object. If we want to grab an object, then maybe we want to run the claw motor for 2 seconds. And in order to do that, that could actually be really simple in an imperative language, like that flowcharting language I showed you earlier, because you would just add a block that says run motor, wait 2 seconds, and then do the next thing. But this is a reactive application. We're getting new input all the time, and we're updating every single cycle. So you can't just have blocking calls like that. So instead, you just have to remember, well, when did we start moving? And then every update, You say, are we done yet? Are we done yet? Are we done yet? Oh, now we are. We can go back to idle. And again, you'll find little state machines in the control logic. Similar to the claw, if you want to move forward by a certain amount, you need to remember where were you when you started, and what should the positions of the motors be when we get there. And then again, every update ask, are we there yet? If so, now we're idle again. So control is much like perception. It's often very functional. And again, there's often these little state machines in there. And so it's really, really clear exactly what information each control state cares about. It's usually a small amount, but it's nice to know, well, if the robot's not doing what I think it should be doing, is that like a stateful problem, or is the bug somewhere else? Especially when you have stateless control logic. If the robot's not doing what you think it should be doing, it's unlikely that the bug is in the control logic. Control is often also layered. So even at the operating system level, when we say set the speed of the motor, there's another control loop under there that I'm not even worrying about, but it's doing its own thing, and then I'm telling it set the speeds of the motors and kind of having this abstraction of the different control states, grabbing, follow the line, that the robot can be in. And we're going to build on top of that and add behavior to this, where it's going to decide, well, we have all these different modes that the control state should be in. Which one should I be in right now? What should the robot be doing? So that brings us to behavior. And behavior really is like the core of your Elm application. When I thought, let's try Elm on a robot, I thought, perception would be nice to do with Elm, and control would be nice to do with Elm, but yeah, behavior, that's where the type system and pattern matching, that's where I think it'll really, really shine. So for the challenge we've set out for ourselves of go around the island and feed people to sharks, there's these 4 different behaviors that are involved in there, and robots got lost. There's an initializing mode where the robot had to open and close the claw in order to calibrate it, and then it says, well, now I want to find an object. And once you've found an object, it's going to grab it. Once you've grabbed an object, now you're going to carry it for a while until you figure out, does it need to go left or right? And once you've figured that out, which you might know already, then you can say, okay, now I'm going to remove the object. So this is different than the lower level control logic that just says, I'm going to follow the line right now. There's really no, you're following the line, yeah, but like why? The behavior is what says why. What are we trying to accomplish? So that becomes our model. Right? The robot can be in these 4 modes. And again, some of them have no state, some of them have a little bit of state. Behavior is also the update function. So every time we get new inputs and we update our perception, and we update the current, we look at, well, what's the robot currently, what's the control state? Is it following the line or is it idle? We can update behavior. And so when we call that function, we get, okay, current behavior, here's the new behavior, and then maybe we want to replace the current control state and say, okay, we were following the line, but now I want you to close the claw. So one of the things I strive for in this kind of behavior logic is that it should be readable. You should, yes, there's syntax here, but if you know the syntax of Elm, then if you were describing how the robot works to somebody, that should just be kind of conveyed right there in the code. So if the robot is trying to find an object and the claw is open and it bumps into something, then it should grab it. And that's kind of what the code says. And if we were finding an object and the claw has been closed, then now we're carrying an object. And otherwise, just follow the line. And I feel like if I didn't have code on the slide and we were just watching the robot, that might be how I describe its logic to you. And if you are familiar with Elm syntax, hopefully that just kind of comes across very plainly in the code. Some behaviors have parameters associated with them. So again, if we're currently carrying the object and we want to then remove it from the island, we need to know what direction. So if we're carrying it and the perception module doesn't know which direction we're going, then we should just keep following the line, because that remove object function that instantiates a new behavior, it requires a parameter. So only if we are carrying the object and the perception module knows which way we're going, then we can say, okay, let's go into the remove object behavior. Which brings us to something that sequential actions are slightly awkward. I alluded to this earlier, but when we find an obstacle, we need to go through a bunch of steps. We're going to need to grab it, turn, move forward. We're going to need to let it go, move back, and then turn back, and then carry on our way. But at the same time, we're getting, our update function is being called again and again and again. So we need feedback from the control module. This is why the control module has to get updated before behavior. Let me go back a couple, but that, remember that removing object behavior, if we're in that state, then we also have a list of these control actions. Those for, 4 or 5, turn, move, and let go, and go back. So this is something that would be really, really easy to express in some imperative languages, but it is a little bit awkward here, where we need to constantly be checking, is the control module idle? If so, and do we have a next action? Okay, just do that. If we're idle and we don't have any actions remaining, then great, we're done. We can go back to finding another object. If the robot's not idle, like maybe it's in the middle of opening the claw, or maybe it's in the middle of a turn, then just carry on doing what we were doing. In a way, this is like kind of creating emulating a imperative language inside of a functional language, which is a little bit weird, but there are trade-offs. So to wrap up behavior, behavior is stateful. It kind of has to be. If your behavior isn't stateful, then there was probably no point in having behavior. You could have just done perception and control and said that it's a purely reactive system. It's also symbolic. So you might notice that there's really no numbers, there's no thresholds in the behavior logic. If you push all that to the perception, then when it comes to behaviors, you can just talk purely in terms of qualitative values. And ideally, behavior should be explainable as well. And if the code is using symbolic values and things with nice names rather than looking at thresholds, then hopefully you can read the code and see exactly what, and it describes exactly what it's doing. So, does this work? I'm going to bring us back here, and we're going to get cozy again. There's a robot, and I'm going to stick an object in front of it. I'm going to turn this around. Ooh. Come on. There we go. So when it finds an object, we'll grab it. In this case, it knows which way it's going, so it can turn, carry it away. Let that go. Go back, and now we can carry on. All right. Oh. I just lost my mic. So, how are we for time? Real quick, the other thing here, when I said it should be explainable, here the robot is showing which behavior it's in at any given time step. So you can see it was trying to find an object for the whole talk, and then you can see during this period of time it was removing the object. So did it work? Cool. So wrapping up, I want to go back to those 3 questions I asked. Can we use Elm to program a robot? Yes, it does work. Is it effective? This is interesting. I think that this is actually 2 questions. One is it an effective platform for robotics? And the other one is Elm an effective language for robotics? And these are different things. The answer to is it an effective platform is maybe a little less clear. In this case, it actually is a really heavy software stack to run on this hardware. This thing is quite a bit less powerful than a Raspberry Pi. So, for example, when Node.js does a garbage collection, that takes like a decent chunk of a section, and sometimes the robot can get lost during that time. But that's kind of incidental. That's kind of unrelated to my original goal, which is to say, is Elm a nice language? And I think it was. I think that Perception is often involves some amount of state, and Elm makes that very explicit. Behavior involves a lot of state machines, and custom types and pattern matching is really great for that. And treating control as like a declarative approach to control has a lot of the same benefits as a declarative approach to views. That what the robot's doing always reflects its internal state and its intentions. So I think it was an effective language for robots. Is it delightful though? That's subjective, but I really enjoyed it. I think it was. And if this interests you and it's something that you think you might want to explore, I'd encourage you to take a look at the code and see if it resonates with you. The code's online. You can find me on Slack as Deschamps. That's my email if you want to get in touch. With that, I'd like to say thank you to Matt Griffith for mentoring me through my first talk, as well as Mike Onslow, wherever you are, and the rest of the Elm Detroit meetup group for giving me a lot of helpful feedback. If you're ever in town, come say hi. And that brings us to lunch, and so I'd love to talk to you, so come find me, and thank you very much.